Hello everyone. Today I'd like to introduce you to the static module in the Easy software. Using the example of the 4-point sail, which was already explained in the first steps, form finding section, I'll show you how easily a static analysis can be performed. We are still working within the project path of the 4-point sail. In the Easy shell, program modules are organized in tabs. The static analysis module is now being selected. Within the graphical user interface, a tile labeled the Easy Static Program is available. The program is launched by clicking this tile. When activated, the static program opens in its own separate window. You can choose between creating a new model, starting with an empty model, or opening an existing one. In the New Model dialog, we change the name of the database. The files to be imported, the input file, triangle file, and polygon file, can be selected individually. In our example, we use the default files that were generated during the form finding process. The reading process is started via the Create button. The graphical user interface features a menu area. A quick launch toolbar located beneath it offers key controls for simplified operation. The window is divided into several sections. In the center is the main graphical interface. On the left is the Properties window. On the right are the corresponding options, with the Project Explorer located below. At the bottom is the Information area. Before performing a static analysis, appropriate materials and cross-sections must be added to the project. This is done by clicking the Open Material Profile Database icon in the toolbar. The database window will then open, allowing you to choose existing entries or create new ones. The first step is to select the required materials. To choose a membrane material, set the filter to Membrane. Then, from the list, select the material named TechNetX Default. The properties of the selected material will be displayed on the right side of the window. Click the Add to Project button to add the material to the current project. Once added, the material appears in the Project Explorer, located in the bottom right corner of the main window. Another important component is the cables. A suitable material must also be selected for this. To do so, set the filter to Cables. Now select the material, Cable Material, Steel 160, from the list. Alternatively, you can add the material to the project directly by double-clicking it. It will then appear in the Project Explorer in the lower right area of the window. After selecting the material, an appropriate cross-section for the cable must be chosen. To do this, switch to the Cross-Section tab. Use the filter to narrow the selection to Cables. From the list, select the cross-section RedILEOSS8. Its properties and a schematic view of the cross-section will be displayed on the right side of the window. The appropriate material profile is automatically assigned to each cross-section based on the predefined materials. Click the Add to Project button to add the selected cross-section to the project. It will then appear in the Project Explorer under Cross-Section in the lower right section of the main window. Corresponding cross-sections were already created during the material selection for the membrane. The database can now be closed. The perspective view is controlled in the same way as in Formatted. To change the view perspective, click Rotate Pan Zoom in the Quick Access toolbar. Alternatively, you can adjust the view by clicking and holding the right mouse button. Once all materials and cross-sections have been added to the project, they must be assigned to the corresponding elements. To do this, activate the Select Anything tool in the Quick Start toolbar and click on the central point labeled 1 in the graphical interface. The properties of the selected surface will then appear in the menu on the left side of the window. Next, the cross-section must be assigned to the surface. To do this, open the drop-down menu next to Cross-Section 1 in the Properties panel and select TechNetX Default 1000. The second cross-section is automatically assigned TechNetX Default 2000. After the assignment, the link attributes must be recalculated, meaning the initial lengths are determined based on the material properties. This is done simply by clicking Calculate Link Attributes. Next, the cross-sections of the border cables must be assigned. To do this, select the icon Select Sets of Links from the Quick Start toolbar. In the graphical interface, click and hold the left mouse button in the upper left area of the view. Then drag a selection box across the entire object. Release the mouse button to mark all contained link elements. You can now change the cross-section for the selected set of links in the Properties panel, or alternatively, select the individual links first before assigning the cross-section. By clicking Select Links in the Properties panel, the view switches to the Link properties. In the cross-section drop-down list, the appropriate cross-section can then be highlighted and selected. To deselect the marked links, activate the Select Anything function in the Quick Start toolbar. Then, simply click in an empty area of the graphical interface to clear the selection. All components of the 4-point sail are now assigned the appropriate materials and cross-sections. This completes the basic setup required for static analysis. The next step is to create a load case by clicking Add Load Case in the Quick Start toolbar. The newly created load case LC1 appears in the Properties panel. It is left unchanged for now, and the analysis can be executed directly. This calculation generates the materialized result of the form finding process. To start the calculation, click the Create Result button in the Quick Start toolbar. After the calculation is completed, the result is displayed in red. For improved visualization, the surface of the original model is deactivated in the Project Explorer. The mesh remains visible. Right-clicking on the graphical interface opens the View Context menu. From there, the front perspective is selected. You can now zoom in using the mouse wheel to visually compare the two meshes, the form-finding mesh and the materialized calculation mesh. No differences are visible. Now the view can be switched to top view, and the surface display can be reactivated. To analyze the static calculation, stresses, forces, and deformations can be visualized graphically. This is done by clicking the Analyze Result icon in the Quick Start toolbar. Once selected, the relevant display options appear in the Options panel on the right-hand side. In the Membrane tab, enabling the Link Stress toggle displays the stress distribution in the membrane using color shading. The visual range can be fine-tuned using the slider next to it. The displayed stress distribution reflects the mesh property presets that were defined during the initial form-finding step covered in the first video. The legend displayed in the graphical interface shows the stress distribution using numerical values. In the pre-stressed state resulting from form finding, the value is close to 1, with only slight deviations at the high and low points. The previous calculation was solely used to verify the form finding result. Now the same load case will be used to calculate the self-weight load. To do this, rename the load case in the Properties panel to LC1, Self-Weight. Then scroll down and enable the checkbox Apply Dead Load. The calculation can now be run again. In the graphical interface, the membrane stresses resulting from the self-weight of all components are displayed using color shading. When the deformation shape from the calculation is compared point by point with the original form-finding model, a difference becomes apparent due to the self-weight. After analyzing the first load case, a new one is created. This is done as before by clicking the Add Load Case icon in the Quick Start toolbar. The new load case is then renamed to LC2 Snow in the Properties panel. To apply a snow load, click Add in the Area Load section. This creates a new entry 1, marked with a red background in the list on the left. Double-clicking this entry opens the Properties window for editing. Under General Information, select Snow from the Load Type drop-down menu. Click on Value in the Parameter section and set it to 0.5 kilonewtons per square meter. The load must be assigned to a surface. To do this, select Add All under the Elements section. All parameters for the load case are now defined, and the calculation can be started by clicking the Create Result button. The colored surface initially obscures the result. By clicking once on the graphical interface, the selection is cleared, revealing the stress distribution within the membrane. Under Snow Load, the membrane stresses increase in the area between the two high points. To analyze the deformations, the view is switched to front, and the surface is deactivated in the Project Explorer. By zooming into the center of the membrane, the deformed shape, in red, becomes clearly visible compared to the pre-stressed state, in green. The membrane has noticeably sagged. After re-enabling the surface in the Project Explorer, a new load case can be created by clicking the Add Load Case icon in the Quick Start toolbar. The load case is then renamed to LC3 Wind in the Properties panel. As before, An area load is added by clicking the Add button next to the list field. The familiar red highlighted 1 appears in the list and can be opened for editing by double-clicking it. This time, wind is selected from the Load Type drop-down menu. In the now available input parameters for wind, the velocity pressure is set to 0.65 kilonewtons per square meter. For simplicity, the CP value is left at its default setting of 1. This time, the From Surface option is used to select the area. All parameters for this load case are now defined, and the calculation can again be started by clicking the Create Result button. As before, a single click on the graphical interface clears the surface selection. Switching the view to front makes the deformation at the center of the membrane clearly visible. In the wind load case, the membrane is lifted due to suction. The deformed result is shown with a red mesh, and the original model is displayed in green. To analyze the membrane stresses, they must be re-enabled using the toggle button in the Options panel. After switching to the top view, the membrane stresses caused by the wind load become clearly visible. Compared to the snow load, the stress distribution under wind load is oriented orthogonally, with increased membrane stresses in the area between the two low points. This becomes more visible by changing the perspective using mouse movement while holding the right mouse button. By adjusting the scale using the slider in the Options panel under the Membrane tab, the visual representation of the stresses can be refined. The maximum membrane stresses can be read directly from the legend in the bottom right corner of the interface, as it is automatically scaled. In this example, the maximum value is 8.16 kilonewtons per meter. The static analysis of the 4-point scale is now complete and can be saved. This is done by clicking the Save All tile with the disk icon in the Quick Start toolbar. Afterwards, the static analysis module can be closed. Thank you for your attention. In the next video, we will take a closer look at the cutting pattern generation for the analyzed 4-point sail, with a detailed explanation of how easily it can be created.